Upgrading front-end tooling usually nets a development team a 5 to 10% speed increase. With the release of Vite 8, the standard for web compilation has moved to a toolchain built in Rust. This horizontal bar chart compares official synthetic compilation benchmarks. When processing a massive application containing 19,000 distinct modules, the legacy Rollup bundler took 40.10 seconds. The new Rolldown engine processed the exact same workload in 1.61 seconds. To confirm this holds up outside of a synthetic environment, we can look at deployment telemetry from major engineering organizations. Software company Linear saw their production builds drop from 46 seconds to 6 seconds, an 87% reduction, while platforms like Beehive and Ramp documented reductions of 64 and 57% respectively. Dropping compile times by a factor of 25 does not happen through minor adjustments. It requires discarding the dual bundler architecture that Vite relied on for years. When Vite originally launched, large codebases were bottlenecked by monolithic bundlers. To solve this, the framework's creator split the compilation lifecycle into two distinct phases, making a pragmatic engineering bet. For local development, the system used esbuild. Because esbuild was authored in Go, a compiled systems language, it could serve unbundled native ECMAScript modules, the standard format for packaging JavaScript code, at speeds the previous generation of tools couldn't reach. But esbuild lacked the mature plugin ecosystem required for complex edge cases like dead code elimination and chunk splitting. So for production builds, the framework handed the process over to Rollup, a bundler written in JavaScript. This meant Vite was maintaining two distinct transformation pipelines and two separate plugin systems. The core maintenance team was forced to write an increasing volume of glue code to keep the behaviors of the Go-based development server and the JavaScript-based production build aligned. Despite these efforts, developers frequently encountered subtle behavioral discrepancies. An application would compile perfectly during local development, but behave differently once deployed. Managing asynchronous plugin states across disparate programming languages created a hard computational ceiling. To break it, the ecosystem needed a rewrite. The mechanical flaw limiting Vite's speed existed at the data level, right at the boundary between Go and JavaScript. For a plugin to process a codebase, it must first convert the raw text into an abstract syntax tree, or AST. An AST is a data structure that maps out the logical relationships of every piece of code. Generating this tree structure inside a high-performance native engine like esbuild is fast. But to apply a custom JavaScript plugin, the engine has to hand that tree over to the JavaScript environment. Because Go and JavaScript handle memory differently, the native engine must serialize the entire abstract syntax tree into a JSON string. Once the data crosses the boundary, the JavaScript side must parse that string of text back into a usable object. This continuous translation of data back and forth negated the speed advantages of using a native compiled engine. To eliminate this serialization bottleneck, the entire compilation lifecycle must execute within a single, unified memory space. To achieve this unified memory space, the Vite team rebuilt the architecture using Rust, a systems-level programming language. Rust provides the computational speed of C++, but with strict compile-time memory safety guarantees, making it effective for processing massive JavaScript codebases. The bedrock of this new architecture is Oxy. Oxy is a suite of JavaScript language tools written in Rust. It integrates a parser, a resolver, a transformer, and a minifier, all operating within the same environment. Because these tools exist in a single memory space, they can share the abstract syntax tree directly. This visualization demonstrates the efficiency of the Oxy foundation. It compares the formatting tool Oxformat against the industry standard Prettier. By avoiding constant serialization, Oxformat achieves 100% behavioral compatibility with Prettier while executing 36 times faster. By standardizing on the Oxy parser, Vite 8 ensures that your linter, your formatter, and your bundler all read your code using the same underlying logic. Built on top of this Ox foundation is Rolldown, the engine that replaces both esbuild and Rollup in the Vite 8 pipeline. Rolldown was engineered to achieve sub-second execution speeds while maintaining absolute ecosystem compatibility. To achieve this, the Void Zero team architected the engine to support the same plugin API used by legacy Rollup. This ensures the custom plugins engineering teams already rely on will function with zero modifications. Transitioning to a unified Rust architecture also unlocks an optimization called raw AST transfer. Rolldown allows custom JavaScript plugins to access the Rust-produced AST directly from memory. This handoff bypasses the JSON serialization bottleneck that slowed down older architectures. Furthermore, the engine introduces a feature called native magic string transforms. Developers can write custom transformation logic in JavaScript, while the computational burden of string manipulation and source map generation is offloaded back to the Rust core. Fusing the flexibility of JavaScript with the execution speed of Rust represents the current limit of modern compiler design. This architecture directly impacts local development in massive enterprise monorepos. A monorepo is a single repository containing multiple isolated projects and libraries. Historically, starting a local server for a large monorepo flooded the browser with thousands of network requests for unbundled modules, causing startup latency. Vite 8 introduces an experimental feature called full bundle mode. Early testing indicates this mode delivers a 3 times faster server startup and a 10-fold reduction in total network requests. By leveraging Rust to pre-bundle development files at native speeds, the engine eliminates the network choke point that previously slowed down scaled engineering teams. To complement the new engine, Vite 8 ships with integrated dev tools to provide immediate transparency into the build process. Engineers can now visually track module transformation flows and explore nested dependency chains. With this data mapped visually, developers can pinpoint precise compilation bottlenecks in real time. This integrated toolchain, Vite, Vitest, Rolldown, and Oxk, has been unified under a single brand identity known as Void Zero. The visual redesign utilizes a distinct Cloud Dancer color palette, chosen to reduce cognitive fatigue during prolonged development sessions. By centralizing the development lifecycle within a single unified Rust engine, Vite 8 resolves the structural inconsistencies of the past and closes the gap between local development and production deployment.